Hey everybody. So we're going to continue the 3.3 notes. So this is like 3.3 part 2 or day 2. If you have not watched part 1, don't watch this one first. It won't make any sense to you. You need to go back and do the other one first. So what we learned in part 1 was the power rule, where you have an exponent, you have a simple function and an exponent, and you are able to take the derivative of it without using that long limit definition of derivative. Much easier. And now, today we're going to learn how to use a similar rule to do products and quotients of two functions. I'm going to show an example right here of why you cannot just use the power rule for products and quotients, all right? So what I'm writing is a test, okay? This is only a test, all right? Test. So I'm telling you ahead of time, it's not going to work out. So if we did the derivative with respect to x of x squared times 3x, if we did this with the power rule that we just learned in day 1, and did them separately and then just multiply them back together, let's see, what would we get? Well, the derivative of x squared would be the 2x, and the derivative of 3x would be 3. 2x times 3 is 6x. Okay, so now let's multiply x squared times 3x out and see if we get the same derivative. So this time, if we start with, instead of x squared times 3x, let's say 3x cubed. See, I just multiplied that together. Now this is a simple one function, so let's take the derivative of that. Well, the 3 would come down, you would get 3 times 3 is 9x squared. Not at all, not even close, the same thing between these two. So, moral of the story is, this method right here does not work. You have to either create one function by multiplying everything out or dividing everything and get you one function, or you have to use what we're going to call the quotient and product rules, okay? And they're a little, they're not complicated at all. You just have to learn them. Let's just say that. You just need to know them. There's a pattern to them, just like the difference of two squares or something like that. Okay, so let's look at this page here, the product rule. Quick side note. From here on out in calculus, we will often be referring to different functions as u and v. I'm not sure why they picked u and v, but it's extremely common. I remember when I was in high school and we were doing calculus derivatives, we used u and v back then too, so it's something that's been around for quite a while. So u and v are nothing more than, this means one function times another function. Okay, so, and they're both in terms of x because it's derivative with respect to x. So here's the product rule. The product rule is when you take the derivative of one function times another function, the answer is, the derivative is the first function just by itself, you didn't do anything to it, times the derivative of the second function plus the second function times the derivative of the first function. These two rules right here, these two things, they say the same thing, okay? U v prime plus v u prime is the same thing as u dv dx plus v du dx. All right, so let's see how this would work. It says here, for polynomial functions, it is not always necessary to use the product rule. However, with trigonometric, exponential, logarithmic, and other function, it is a necessary tool. Why would it not be necessary for something like this? Well, you could go ahead and multiply everything out. You could simply just get one function if you wanted to. So let's try that first. So first, if we multiplied everything out, we would get y equals, so I'm foiling it out. I would get y equals, let's see, 15x cubed plus 10x to the 7/2 power minus 21 minus 14x to the 1/2 power. If you are having trouble with exponents, this might be a really good time to go find a YouTube video about multiplying exponents. But here we're not raising this exponent to a power, actually saying x to the 1/2 power times x to the 3 power, which is, I'll just come over here and do this, x to the 1/2 times x cubed. What do you do when you multiply exponents like this? Well, you add them. So this is going to be x to the 1/2 times, if I get a common denominator, instead of 3, I would have 6/2. So that when you multiply those together and you add the exponents, you get x to the 7/2 power, which is where this came from right here. All right, if you're having problems with that, please, please, please don't think it's going to go away, because it's not. Here on out, we use a lot of exponents, and we need to know how to multiply, divide, and combine them using products and exponents. All right, anyway. So that is my function written as a single function instead of the product of two functions. So what would I take? How would I take the derivative of that? Well, I would just use the power rule. So it would very simply be 45x squared plus, now when you bring the 7/2 down, you'd have 10. I guess I'll just do it kind of the long way. And then 7/2 minus 1 as your exponent. I'm going to clean all this up in a minute. Minus 21. Minus 21, the derivative of that is 0. The derivative of any constant is 0. So that goes away. And then the 14x times x to the 1/2 power, the derivative of that would be negative 14. Bring the exponent down, and then your new exponent is 1/2 minus 1. All right, so how would we clean that up? Let's see, it would be y prime equals 45x squared plus 10 divided by 2 is 5. 5 times 7 is 35. 7/2 minus 1 is going to give you 5 over 2, 5/2. And then 14 divided by 2, or 14 times 1/2, is 7. And x to the 1/2 minus 1 is a negative 1/2. Oops, negative 1/2. Okay, so there's our answer. There's our derivative. So it's possible to do it that way. Now, I'm going to try to copy this and put it on the next page so that we can do the next part of the problem, or do the same problem, but again, a different way. Let's see if I can do this. Is that copy? Copy. Yay. Okay. All right, so this time we're going to do the exact same problem. We're just going to use the product rule, okay? And remember, the product rule said the derivative with respect to x of u times v is equal to, go back here if you're not sure, is equal to u, the first function, times the derivative of the second function, plus the second function times the derivative of the first function. Okay, so let's see what we get here. So y prime is going to be equal to the first function, u, just plain u. We don't do anything to it, we just copy it down, okay? I am going to change my exponents to a fraction instead of a square root, because I just think it makes the problem easier in a minute. All right, times the derivative of v. So I need the derivative of 5x to the third power minus 7, which is going to be 15x squared. The minus 7, the derivative of that is 0, so that goes away. All right, plus v, which is the original v, and then times u prime. Well, the derivative of 3 is 0. The derivative of 2 to the 1/2 power is going to be 2 times 1/2 is just 1, x to the negative 1/2 power. All right, let's clean that up just a little bit. So if we distribute here, we get 15 times 3 is 45x squared, plus 15 times 2 is 30, x to the, now again, we're multiplying exponents, so we have x to the 1/2 times x squared. That is the same thing as 1/2 plus 4 over 2, is that right? So I get 5/2 power, plus here I'm multiplying 5x cubed times x to the 1/2, so I get 5x to the, let's see, that would be 6/2 minus 1/2 would be 5/2 power minus 7x to the negative 1/2 power. All right, clean it up one more time. Let's see if I can combine anybody. 45x squared plus, I can combine these two and I get 35x to the 5/2 power minus 7x to the negative 1/2 power. I hope that's the same thing I had just a second ago. Oh, it is. Good. All right. So we've demonstrated that there's two different methods for taking the derivative of a product. Sometimes you just have to use the product rule. Sometimes, if you would prefer, you are able to FOIL this out, multiply it out, get one function, and use the power rule. All right. Let's look at the quotient rule. This is the one everybody has a little bit of a problem remembering. Well, that's not true. They have a little bit of a problem remembering it at first, and then they never forget it because they've said it so many times. So just go ahead and say it 50 times to yourself and get it memorized now while you can. So we have a shortcut for saying this. Now in your notes, it mentions Snow White and the Seven Dwarfs because of the hi-ho, hi-ho, it's off to work we go. Do you know that song? So we would kind of use that sort of to remember this rule. I don't really sing it like that in my head. But if we remember ho-de-hi minus hi-de-ho over ho-ho. Ho-de-hi minus hi-de-ho over ho-ho. Ho-de-hi minus hi-de-ho. I don't know. Maybe that works for you. All I remember is low-de-hi minus high-de-low. I say low-de-hi minus, whoops, high-de-low over low, low. All right, if this makes no sense to you, let's look at what it means. Low, D, high. That means the bottom one, as in low, the lower function, the bottom function. All right, that's what we're saying here. That's the V function. V is the lower one or the bottom one. So it's low, D, high, low times the derivative of the top one, minus high, D, ho. High being the top function minus the derivative of the bottom function, over low, low, which is low times low, which is low squared. Okay, I am going to use this. Some people just prefer to memorize the derivative of u over v is v times u prime minus u times v prime over v squared. It really doesn't matter how you memorize it. It is important that you memorize it, and it does matter the order of the derivatives on the top here. It is bottom times the derivative of the top minus the top times the derivative of the bottom. That minus sign right there makes it very important that you get the order of these correct. If you look back at the product rule, it doesn't particularly matter which term you put first because there's a plus in between, but on the quotient rule it very much matters, and it won't come out to be the same answer if you mess it up. Okay, so back to the problem. Let's see. Let's find the derivative with respect to x of x times x squared plus 1. We're going to have to use the quotient rule. Even if we didn't want to use the quotient rule, I don't see an easy way to multiply this out in order to get just a single term. So we would have to use the product. I don't see any way around using the quotient rule. All right, so how would we do this? Well, let's see. The derivative is going to be, derivative with respect to x is going to be low, d high, so the bottom, the low, times the derivative of the top, which is just 1, minus the top times the derivative of the bottom over low squared, or the bottom squared, or the bottom times itself. So let's clean that up just a little bit. We would have x squared plus 1 minus 2x squared over x squared plus 1 quantity squared, and that is going to give us an answer of negative x squared plus 1 over x squared plus 1 squared. And no, you cannot cancel these x squareds plus 1 because this one has a negative in front of it. And if you factored that negative outside, you would have negative x squared minus 1, which is not the same thing as you have on the bottom, so we're not even going to do that. So this is a sufficient answer right here. In fact, in calculus, simplifying is not always something you even really need to worry about, so this is fine. All right, let's look at the next one. The derivative with respect to x of 5x squared over x cubed plus 1. Well, what is that going to be? Go back to the rule. The rule is low d high minus high d low over low squared. So low d high, derivative of the top, derivative of high, is 10x minus high d ho over low low. Does that all make sense? If you need to go back and do that again, then go back and do it again. But it's low d high minus high d low over low low. Okay, so let's simplify that, or just clean it up just a little bit. It's not even simplifying, it's just making it look a little prettier. So x cubed times 10x is going to give us 10x to the 4th plus 10x minus 15x to the 4th, all over x cubed plus 1 squared. All right, I got two things on the top I can go ahead and combine, and I end up with negative 5x to the 4th plus 10x all over x cubed plus 1 squared. Okay, once again, we're not simplifying that. That's as good as it gets. All right, let's look at the next page. Second order and higher order derivatives. So the first derivative is what we've been dealing with all along. We've just been taking the derivative one time. That's a first derivative. Well, you can take a derivative essentially forever as long as you have enough exponential power to keep taking the derivative. We call those higher order derivatives. It's pretty common to take a second derivative in this class. We don't, except for just right now when we're learning it, we don't really ever put into practice third, fourth, fifth, or any higher derivatives than that. First and second is about as high as we go in Cal 1. So all you do, though, it's very easy. You just keep taking the derivative. It's not hard. It's not complicated. There's no trick to it. You just continue to follow the same rules over and over and over to get the derivative that you want. So let's look at a couple examples here. If we are given the question that says find d to the 4 or dx to the 4, that means find the fourth derivative, the fourth order derivative, okay, of all this. Well, that just means we need to start with the first derivative and keep working. So let's do that. So the first derivative, y prime, would simply be negative 40 x to the 7th power plus 12 x to the 5th minus 27x squared plus 32. I hope that this part is getting very easy for you by this time, maybe. All right, so then the second derivative, all you do is the exact same thing one more time. The 7 comes down. 7 times 40 is 280. So negative 280 x to the 6th power plus 5 times 12 is 60 x to the 4th minus 27 times 2 is 54. Oops. X. 32, derivative of that is a constant. It is 0. Let's do it again. Third derivative. 280 times 6 gives you a negative 1680 x to the 5th plus 240 x cubed minus 54. Last time. Y to the 4th. That means the fourth derivative, or y, I guess you'd call that quadruple prime, because this is y prime, this is y double prime, this is y triple prime, so I guess that would be y quadruple prime, fourth derivative. Let's see, so 5 times negative 1680 gives you negative 8400 x to the 4th plus 240 times 3 is 720 x squared, and this goes away because it's a constant. So there's our answer. Not complicated, just maybe needed a little calculator or some scratch work. to do the multiplying. Okay, so let's do the next one. Find f prime, double prime of x if this is your function. Okay, so we have a quotient rule. We're going to have to use the quotient rule because we have one function divided by another function. All right, so let's start with the first derivative, f prime of x. F prime of x is going to be low d high minus high d low over low squared. Clean that up just a little bit before you do your second derivative. Let's see, if you multiply here, you get x minus 1 minus x over x minus 1 squared. And that is just simply negative 1 over x minus 1 squared. And before I can do my quotient rule again, I just need to multiply all this out. So f prime of x, my first derivative, is negative 1 over x squared minus 2x plus 1. I just FOILed that out. Okay, so now let's do our second derivative. The second derivative is again a quotient rule, and it's going to be low d high. Well, the derivative of the top is 0. It's going to make all that go away. Minus high d low. The derivative of that bottom is 2x minus 2 over low squared, x squared minus 2x plus 1 quantity squared. All right, when you simplify all this, you get, that goes to 0 because it's times 0. You get 2x minus 2 over x squared minus 2x plus 1 quantity squared. And that's it. That's your answer. All right, let's look at the next one. Find f raised to the fourth. How would we say that? Let's see. We'd say find the fourth derivative of the function x. No, I'm sorry. They want us to find the fifth derivative if the fourth derivative is 2 times the square root of x. So if the fourth derivative is 2x to the 1/2 power, I always change my square roots and things into an exponent before I do the derivative because it makes your life easier. It's easier, easier, easier. So do it. Don't take shortcuts. Okay, so all we have to do now is take a single derivative of this. If we had the fourth derivative and we do it once, then we now have the fifth derivative. So we're going to have 2 times, bring the exponent out front, x to the 1/2 minus 1. Oops. So that simplifies as simply x to the negative 1/2 power. And that is our answer. Okay, that's it for lesson 3.3. Please come to class prepared. We have a lot to do this week, just a lot of practice. Give you guys lots of time to get your derivatives straight. And then we're going to have a test on Friday. Okay.